Welcome back to Separations. In this video, I'll talk about how distillation column problems are typically formulated and the different classes of things that you may be asked to calculate. So the first thing you can do is draw the process flow diagram for a distillation column, very similar to how you would draw it for a single stage flash distillation. So there's really not all that much is different, except instead of V, Y, L, and X, my outgoing product streams are D for the distillate flow rate, XD for the distillate purity, B for the bottoms flow rate, and XB for the bottoms purity. Just as in a single stage distillation, F and Z are typically given because as the separations engineer, you typically know what the stream is that you want to separate. So in just a moment, we'll talk about the three types of distillation column problems that I like to classify. For the design and evaluate type problems, either one or both of XD and XB, the compositions of the distillate and bottom streams would be given. And if there's only one, you'd need to specify D or B as well. And think about why that makes sense. Once again, if you're the separations engineer, you typically know what you want to separate, and that should make sense, but you should also have some type of target purity in mind. So if you have a particular reactant that you want to get to a certain purity in order to be able to sell, or if you have a wastewater stream that you want to remove the presence of a certain purity to release it to the environment, you typically have some idea of what that threshold is. So you have some design target or a specification that you are trying to achieve. And as you're solving these problems, you'll realize that the interior variables, how I call them, of N, big N is the number of stages in the column, N sub F is the feed stage that you're feeding to the column, R, remember, is the reflux ratio, and VB is the boil-up ratio. These will all affect whether or not you can achieve these purities. Typically, you will be able to achieve anything you want if you have a column that has enough stages or has a high enough reflux ratio. So once again, we'll get into how these variables interact with each other in this class and the next few classes. So next, let's talk about the three types of problems. And those three types are going to be the design type problem, the evaluate type problem, and the predict type problem. And just as an aside, these are my own definitions that help me kind of keep clear what the problems are. I didn't get these from anywhere from a textbook, so if you try and look these up on the internet, just be aware that you may not be able to find them. So starting with the first type, the design type problem. This is for situations where the column isn't built yet, and you have to, as the name describes, design it as the chemical engineer. So with this in mind, you usually have some target purities. So this is what I was saying up above for design and evaluate type problems. You'll either have one target purity and a flow rate or both target purities. And your job is to find the combinations of N and R that work. So also note that design type problems may be underspecified. And what I mean by this is that if you don't have a given N or R, then you have a degree of freedom left. So you can choose an R, calculate the corresponding N, or set your N and calculate the corresponding reflux ratio. Typically, I don't like to give design problems that are underspecified like this. So when I give you a problem, typically what I say is I give you what the reflux ratio is and have you calculate what N is. But on a homework problem, for example, I may ask you to calculate the best combination of N and R. And we'll talk about how you would evaluate what combination of N or R, what N and R is better than another combination of N and R. Once again, just remember that N is the number of stages, R is the reflux ratio. So I use this notation a lot. I want to make sure we're getting used to that notation. Second type of problem is the evaluate type problem. So in this, what I mean is you're evaluating a particular existing column for your purposes. So since the column is already built, you have N stages that are set and cannot change. And you also have a target purity. So you're evaluating whether or not this column of N stages can achieve your target purities. And if so, the evaluate type problem asks you to calculate what is the reflux ratio and the feed stage that you should use. And once again, there is a number of different combinations that you can use, and oftentimes you'll have a best combination of reflux ratio and the best feed stage. So typically, you can, while N stages are set, you can move what stage the feed goes into. The third type of problem is the predict type problem. This is where you have the column built already. So your number of stages, your feed stage, and your reflux ratio are all specified. And the question here is what purities will result. So once again, the unknowns here are XD and XB, our main unknowns. So this is the only type of problem in which you don't know or have a specific target purity in mind. So with that in mind, these three types of problems are the types of distillation problems that you will encounter. And keep this in mind as we start seeing distillation column problems, that the solution algorithm is going to change depending on which variables you have and which variables you need to solve. So this is probably a little bit unclear right now. In the last couple videos for today, I'm going to talk about how to graphically design distillation columns. And as I've said before, this will hopefully give you a better intuition of how these variables are interrelated. So in other words, how does the number of stages impact the reflux ratio that you'll need for a given set of purities? Or how does changing reflux ratio change which purities are possible? That will be coming in the next couple of videos. I'll see you in the next video.